Hello, welcome. My name is William Yick, and along with my teammates Lim and Tim, we are a part of the Amistad Lab under Professor George Montañez. And today we'd like to talk to you about bias in machine learning training data. So, as many of you may know, machine learning algorithms are becoming incredibly popular for a variety of tasks. Everything from your next Netflix recommendation that keeps you up till 3 a.m. to the self-driving cars you see on the road today. These things are trained using learning algorithms that learn from massive amounts of data. For the Netflix algorithm, they have data about you, everything you've watched, as well as that information for the millions of other people on the platform. For self-driving cars, they can take information from the surroundings and use that in their learning algorithms. And that is great and all, but this can lead to an issue if the learning data that you give your algorithm is flawed in some manner. And this leads to the garbage in, garbage out motto that is pretty prevalent in AI and ML. And one illustrative example I'd like to show you is this Twitter bot that Microsoft made back in 2016 that was meant to learn from tweets that were tweeted at it and as well as things around it on Twitter to learn about the world. Now, as you might imagine, Twitter is not the best place to learn about the accomplishments of humanity or how to become a fantastic person. And so you can see how this might go wrong. And as you can see on the left here, the bot known as Tay-Tweet started out as a very kind being, but then eventually turned into something much more malicious. And to be honest, the tweet that I have shown on the right here is very low on the spectrum of the things it tweeted. But I can't repeat many of the things that it tweeted for this family safe presentation. So you can just go off of this. Now, for Tay-Tweets, its rampage was contained to the platform it was on, Twitter, and Microsoft was able to take it down within the day. However, sometimes the impacts of AI and machine learning and the ways it can go wrong aren't confined to one specific platform. Take, for example, this algorithm from Amazon that this Reuters article mentions. A couple of years ago, Amazon tried to train a hiring algorithm to classify applicants into a hire this person or don't hire this person group. And as you can see from this article, it went incredibly wrong because it ended up having a bias against female applicants. Now, while the reasons for this are obviously not made public by Amazon, one of the primary reasons that it could have happened is from biases in the training data it was fed. Perhaps Amazon's training data that it was trying to teach this algorithm on were explicitly biased towards men. Maybe it was the data from previous hiring records or even current employees of the company, which might have been male dominated. So clearly, identifying biases is an important issue for classification tasks where we want to put people into this group, or that group. And so how might we do such? Well, one idea is to use hypothesis testing. And we can use this hypothesis testing to look at the training data and determine whether it could be fair in some manner. And the way this would work is you would propose a hypothesis, a distribution that might represent what you think would be fair, and test that hypothesis on the training data. But there are current limitations. The first is that there could be multiple definitions of what fair is, or there might be some leniency in how a person defines fair. Perhaps they're fine with their hiring algorithm hiring 60% of men and only 40% of women because that's within a reasonable range of the 50-50 ideal. So how might you account for this? Well, you would have to test these hypotheses individually on the training data with traditional hypothesis tests, but that can get really complicated because perhaps there could be an infinite amount of definitions of fairness or an infinite range between which you might consider something fair. So testing compound hypotheses gets to be a little bit of a gray area for these traditional tests. The second limitation is in many cases where a hypothesis gets rejected on some training data, the person who tested that might wonder, well, what wouldn't be rejected? What does a hypothesis that wouldn't be rejected or might be considered plausibly explanatory for the data look like? And that's where our work comes in. So we are using what we call two distribution specified complexity hypothesis tests. And they were developed by work in our lab in 2018. And we seek to use these to test for fairness in training data in a unique way that resolves the previous issues that I talked about. So here's the rundown of how it works. The first thing you need to know is that this kappa of x term you see on the left is known as the specified complexity Cardis. And we would like this Cardis to capture two aspects of an observation, which is the little x you see. And this is why we call it a two-distribution hypothesis test. The first aspect we'd like it to capture of the data is the probability that x occurs under some probability distribution p. This is the complexity term of the Cardis, which we denote by p of x. The second thing we wish the Cardis to capture is the data's conformity to some pattern, which we call the specificity, denoted by the nu of x term you see in the denominator. And r is just some normalizing constant. Now, I understand that the definition of nu of x that I've just given is a little bit vague, and that's because it has to be in order to describe it in the general sense. The reason why is because that conformity to some pattern really depends on what data you're looking at. You know, take for example, if you imagine flipping a coin 20 times and landing 20 heads, you might say that that sequence of all heads has a really high conformity to the pattern of having many heads, or that it follows this predetermined notion of structure. But in other cases, that notion of structure or pattern might not really apply. So we have to be very careful on how we define it. And we'll talk more about that later. So the really cool thing about this Cardis is that it possesses a very useful level alpha property that lets us use it as a hypothesis test. Specifically, it has the level alpha property can be seen in the bottom right, and it allows us to reject hypotheses if the Cardis for a certain event is less than or equal to an alpha level. Now, this, for those of you who are familiar with traditional hypothesis tests, this is reminiscent of rejecting a null hypothesis if a p-value is less than a chosen significance level alpha. And so, in summary, we can use this Cardis as a test statistic and use it in a hypothesis test. If it is, and if it's less than alpha, we can reject a null hypothesis. And if it's not, then we fail to reject that hypothesis. And the cool thing about this formulation of this hypothesis test that gets us some extra useful results that traditional hypothesis tests wouldn't. The first is that we can tell you what we call a closest plausible distribution if your hypothesis is rejected. So this closest plausible distribution is the closest explanation that wouldn't be rejected by our hypothesis test. So say you propose an explanation and you ran it through the hypothesis test and it ended up being rejected, what it would return you is the next closest thing that wouldn't be rejected. And this could give you a better sense of what's actually happening behind the data, or what process could have generated the data because yours was rejected. And we can do this by using this S term, which you see on the right, which is, for our purposes, defined as the amount you would need to boost the probability of observing X by in order to be considered plausible. Now, I know that definition is a bit convoluted, so to ground that in an example, imagine that same coin we talked about. You flip a coin, which you presume to be fair, 20 times, and you see 20 heads. In this case, what S would mean, it would mean you would need to boost the probability of observing 20 heads by this much in order to be considered plausible. And after solving a constrained optimization problem, we can actually reverse engineer this to tell you the specific probability that you would need to confer on heads, or how weighted your coin would need to be in order to be considered plausible. And how to interpret this is it would mean that in order for your coin to be a plausible explanation for the string of 20 heads, it would need to be weighted at 77.54% chance of heads, as opposed to your fair coin hypothesis of 50%. Now, for a simple example like this, you know, this solution might be trivial, or this result might seem kind of obvious, but for larger data sets that are not binary, you know, for a coin, it's either heads or tails, for ones that have many, many more outcomes, finding this answer for a traditional hypothesis test is a very difficult thing, which is why we think this is our main contribution to the current research. Now, the entirety workflow of our hypothesis test is shown here, and while it's quite convoluted, I'm going to hand it over to Tim, who will talk you through a slightly more complicated example so you can get a better grasp of how this works. And then Lim will later talk about some additional results, as well as our applications to real-world data sets.
To give a better understanding of our multinomial hypothesis test, let's run through a quick example. Suppose we rolled a six-sided die 60 times. We observed that we rolled 45 ones, 5 twos, 4 threes, 3 fours, 2 fives, and 1 6. To begin our algorithm, we must define our data, valueless, hypothesis, and alpha. In our example, our data is the sequence of faces that we rolled, represented in numerical values. Our value list represents all the possible values that can occur within our observation. In this example, it is the face values of a six-sided die, which are 1, 2, 3, 4, 5, and 6. Our hypothesis is a fair die, which is assigning each face with a 1 in 6 chance of rolling. And our alpha value, which is our probability of rejecting our hypothesis when it is true, is set to 0.05. If you recall earlier in our presentation, in order to compute our Cartus value, we need nu, which captures our observation's conformity to some pattern. To compute nu, we need to know how many events are as or more extreme than our observation. This is captured in our mg of x. However, through research, we realized searching through every possible sequence of our observation can be really computationally expensive. In our small example of 60 dice rolls, there are 6 to the 60, which is approximately 10 to the 46 sequences we would need to generate and check for. In a real-world application, such as hiring records with thousands of applicants, this method can become very daunting. Our solution to this problem was to convert our observation into count vectors and to use some combinatorial magic, as we like to call it. For example, our count vector would be 45, 5, 4, 3, 2, and 1, representing how many times each face was rolled, or a more general phrase to use would be how many times each value in our value list occurred within our observation. Our expected count vector is computed using our hypothesis as a reference. For the dice roll, we assumed a fair die hypothesis of each face having a 1 in 6 chance of being rolled. This means we expect to see a face rolled 10 times in a 60 dice roll observation. By subtracting our expected count vector from our count vector, we get a mean distance vector of 35, -5, -6, -7, -8, and -9. Using our combinatorial magic, we can figure out how many count vectors deviate from our mean distance vector d. For our example, our mg value is 155,394, which is the number of count vectors or events that are more extreme than our observation under the fair die hypothesis. Using mg to compute our nu of x, we can now compute our Cartus. If you recall from earlier in the presentation, the Cartus can be found by dividing our p of x, which is our complexity value, by our nu of x, which is our specificity term, and multiplying that value by r, which is our normalizing constant. We get our Cartus value. If our Cartus is less than or equal to our alpha, we reject the hypothesis. For our dice example, our Cartus is 1.0832 times 10 to the -19, which is less than our alpha value of 0.05. This means we reject the fair die hypothesis as a plausible explanation for our observation. Since we reject our hypothesis, we now compute our S lower bound. S represents how much an explanation needs to boost the probability of observing X, our observation, in order to be considered a plausible explanation. Recall from earlier, we can compute our S lower bound by multiplying nu of X by our alpha and dividing that by the value we get from multiplying R by our P of X. In our example, we get an S lower bound of 4.6157 times 10 to the 17th. This means any plausible explanation must boost the probability of observing our count vector by roughly 18 orders of magnitude or more compared to a fair die hypothesis. Lastly, we compute our Q. Q represents the closest plausible hypothesis that can explain our observation. We define closest in terms of the distance from our original hypothesis, which in our example is the fair die hypothesis. We find Q by using constrained optimization. Our two constraints are that Q must sum to 1, since our hypothesis is a probability distribution. And the next constraint is that Q must satisfy our S lower bound in boosting our original hypothesis. Using gradient descent, we bring Q as close to our original hypothesis while still satisfying our constraints. In the die example, our Q distribution is 0.47, 0.13, 0.12, 0.11, 0.09, and 0.08, which represents the closest plausible hypothesis for our observation. Our Q suggests that our die is more biased towards rolling a 1 and biased against rolling other face values. Our algorithm ends by returning the Q distribution and the S lower bound. You may be wondering, what happens if our original hypothesis is not rejected? Let's revisit our die example. However, instead, we know that we have a weighted die that is biased towards rolling 1. We craft a new hypothesis, placing more weight on 1, a 4 in 6 chance of occurring in our observation, with 2 having a 1 in 6 chance of occurring, and every other face having a 0.25 in 6 chance of occurring. We use the same alpha and are able to compute a new MG of X of 7,017,074, which again is the number of count vectors or sequences that are more extreme than our observation under the given hypothesis. Using MG to compute nu, we compute a new Cardis value of 5,774.95, which is greater than our alpha value of 0.05. Therefore, our hypothesis is not rejected. Since our hypothesis is valid, we return the Cardis and the alpha value at which our hypothesis was not rejected. This would conclude our multinomial hypothesis test algorithm. I'm going to pass it to Lim, who will go through our binomial hypothesis test and some really cool real-world results that we have found.
In addition to our multinomial workflow, we also have a binary hypothesis test. And this lets us actually take some data with a variable that can take more than 2 values, split those values up into 2 categories, and then perform a binary hypothesis test upon those 2 categories with tighter bounds than our multinomial. And while this is largely the same as our other test, it varies in 3 specific locations. Now, the first of these is the data binarization. So you select some values that you think your data might be biased towards, and then all the others are your non-selected values. So those are your 2 categories, selected and not selected. So if our die data, if we thought that was biased towards 1 and 2, and we plug that into our binarizer, you would end up getting the count vector 50 selected values, 10 not selected values. And then our binary Cardis test. Ultimately, the Cardis here takes the same form. Cardis of x equals r, the normalizing constant, times the probability of x over the specificity of x. But each of these subunits has a different formula, which gives us tighter bounds and more power in the binary Cardis. So if we reject some hypothesis, we move along and end up in the binary Q finder. And similarly here, we use constrained optimization to get a plausible distribution that is close to our original hypothesis. But again, because we're working with a binary situation here, we can get a tighter probability bound and more, I guess, power in the distribution that we return. And you might be saying, hey, why not use an exact binomial? Those exist and we know that they work. And quite frankly, it's time. Binomial tails, at least in the manner that we're used to computing them, are rough on computers for a large n. So to compute a binomial, you have to compute n choose k, which involves a calculation of factorials. And because it's a tails sum, you have to repeatedly calculate n choose k. And when you optimize to get a q distribution, you need to do repeated tail sums. So that's just a lot of factorials. And because we're working with large numbers, that is painful for the computer. You can approximate factorials with Stirling's approximation, but you've still got huge numbers flying around, and that's relatively rough on the computer. And here I want to illustrate the difference between the tests. I'm gonna scooch. There we go. Okay, I don't know if that'll show up in the recording, but the difference between the tests here is that the binary test has extremely tight bounds, although the exact binomial is even tighter than that. And FSC is good, but below the others. So on the right here, table 1, these are both pulled out of our article. We have for different sizes of data sets, and different alpha values, how many successes do you need for these 3 tests to start rejecting things? So the exact binomial starts rejecting lower than BSC, which rejects lower than FSC. So again, that illustrates that the exact binomial is more demanding. Our second table is what percent of successes do you need? With a certain percent of successes, what Q distributions are returned? And this percent of successes, probability of success returned. And again, the exact binomial returns a higher probability than BSC, than FSC, because it's more demanding of the data. And now we're going to take a look at some real world data. So this is the COMPASS data set that we're looking at. And COMPASS is Correctional Offender Management Profiling for Alternative Sanctions. And it's a commercial algorithm that's designed to assess the risks associated with an offender, someone who's been charged with a criminal act. So you have violence, recidivism, which is the risk of committing another crime, and the failure to appear in court. Those are the risks. And this became well known, this data set, when it was analyzed for bias by journalists at ProPublica. And it has also been used as training data for other models in order to highlight its bias. But we're analyzing the output of the algorithm directly, so there's no confounding of where the bias came in with this data and the other models that were trained on it. And so for us, what we did is we looked at the scores that are given, can either be high, medium, or low for each of those 3 scores I brought up. And we analyzed both the recidivism score alone and the total score overall. And you may notice that the proposed distributions here are not uniform. So we got these from the proportion of Caucasian people placed into these 3 categories. Because if the entire upstream flow to this point, as in society, and then the training data, and then the COMPASS algorithm itself were fair, African-American offenders and white offenders would be placed into these categories with the same processes and would therefore end up being assigned with roughly the same proportions. But as you can see, both the proposed hypotheses were rejected, and our plausible distributions show less African Americans being placed into the low category and more being placed into high or medium. And so here's some other advantages of our tests. They're very fast. They can run on a consumer laptop, even my beat up Mac with 50 tabs open. They have a high degree of interpretability with our returned Q distribution, allowing you to know in what direction the bias lays. We can inject groups of hypotheses with our lower bound on S, and you don't need to know what shape your probability distribution takes, like in students T or chi-squared. You just need to have some sort of sense of what probability each value has. Thank you for listening. And while this isn't a live talk, still feel free to send us questions if you have any.